Hello, and welcome to the Frontiers of Physics lecture series. We're so happy to have so many of you here from the University of Washington, from Seattle, from beyond, from Port Angeles High School. Welcome back. My name is Marilena Laverty, and I'm an associate professor in the physics department here at the University of Washington. My own research is in the field of cosmology, which is very much related to and inspired by the subject matter of our speaker. Oops, I should have switched to the subject matter of our speaker today, Professor Catherine Freese. So the Frontiers of Physics lecture series started in 2016 and allows us to bring scientists that have made some of the greatest discoveries of our time to Seattle to share with us the history, the context, and the excitement of their work. These speakers have included 10 Nobel laureates, 3 of our own faculty who received the 2021 Breakthrough Prize in Fundamental Physics, and many other luminaries at the forefront of scientific discovery. The topics covered range from the smallest to the largest scales in the universe, from discoveries that have fundamentally altered human technology to those that have changed our understanding of where humans fit into the universe as a whole. This lecture series is made possible by the vision and generosity of Dr. Patrick O'Hara and Dr. Katerina Randolph, and comes together with the work of a diverse group of faculty and community members. Our speaker today is Professor Catherine Freese. Professor Freese is the director of the Weinberg Institute for Theoretical Physics at the Texas Center for Cosmology and Astroparticle Physics at the University of Texas, Austin. Dr. Freese is known for her numerous creative contributions to our understanding of the universe, in particular, the fundamental puzzles of dark matter, dark energy, and the origins of our universe. She has proposed tests of dark matter that are used by experimentalists today, as well as some of the most compelling models for the origin of our universe that remain under active study. Professor Freese earned her bachelor's degree in physics from Princeton University and her PhD in physics from the University of Chicago. She has held positions at the University of Michigan, the Massachusetts Institute of Technology, and served as the director of the Nordic Institute for Theoretical Physics. She is currently the Jeff and Gail Kodowski Chair at the University of Texas, Austin. Dr. Freese is a member of the National Academy of Sciences and a recipient of the Lilienfeld Prize from the American Physical Society for her groundbreaking research at the interface of cosmology and particle physics and her tireless efforts to communicate the excitements of physics to the public. Dr. Freese is also author of a popular science book, The Cosmic Cocktail, 3 parts dark matter. And I mentioned that, so following our lecture, we'll have a brief Q&A led by my colleague, Professor Alvaro Chavarria, and after that, there will be an opportunity to purchase the book and have copies signed by Dr. Freese. A couple of logistical things. Recording of the lecture is not permitted. Please remember to silence your phones. And then please join me in welcoming Dr. Freese.
Thank you, Marilena, for this lovely introduction. And thank you all for being here. And the first thing I want to check, can you hear me? No? Oh, okay. Well, I don't know. I also have to get used to this system of changing slides. I guess I should point this way. It's already not working. Why not? Oh, you actually cannot hear? Do I need to switch the, do I need to put it in the other setting? It is switched on? Well, he's going to be here, let him do it. I don't know which way's on. I didn't change it after we were doing it.
Oh, it's on.
Yeah.
Where's the, oh, it's not here.
Where is it? Okay, the mic has disappeared. We have to deal with this. In darkness. The power of darkness as usual. Okay, so how do we do this? glad I asked. I couldn't hear you. All right, trying this again? Yeah, can you hear me in the back? Should I do what? They telling, is it, oh, I think it's working now. Yay! You know, I'm glad I asked whether it was working or not. Okay, so before I start talking about modern cosmology, let me remind you of something, which is, let's go back 100 years. That's when all this business started for our work that we're doing today. If you go back into antiquity, I have no doubt that people asked a lot of the same questions. Where are we going? What's out there? What's in the future? Da 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 da. They had creation myths. Then, circa 1915, once Einstein wrote down the theory of general relativity, along came our creation myth, the hot Big Bang. But the difference is that it's correct. I mean, that's just phenomenal in human history. That's a phenomenal achievement. I'm being very serious about this. It's a really, really, really big deal. Now, it's imperfect, and we work to try to fix some of the problems, but I think it's just a major achievement of humanity and I just wanted to start with that. Well, after the equations of relativity in 1915, there was, sorry, I have to find the laser pointer. Here we go. These guys applied the theory to the universe as a whole, and assuming just a few symmetries about the universe, found that there were 3 possible solutions to the equations: expanding, contracting, or static universe. Einstein liked the idea of an additional symmetry of having the universe be static, unchanging with time. But that's just not the way the world is. So Edwin Hubble was using the telescopes above Pasadena, Mount Wilson Observatory, and he made a lot of astonishing discoveries. One of them was he was the first to prove that there's anything outside our own galaxy. People used to think that everything we're looking at is part of the Milky Way. Well, it was very clearly these things were too distant, could not be. And then soon after also was proving that the universe is expanding. So the way that he did that was look at atomic emissions in distant galaxies. And so those atoms emit with a certain wavelength. So here's on the surface of the balloon, I've drawn a wave. But then when you observe them, and we know exactly what the emitted light should look like, but then by the time you observe it here, look at that. The wavelength grew. Why? Because of the expansion. Like when you blow up a balloon and you drew a wave on it, the wavelength would get longer. So that's what he saw. And from that, he was able to prove the universe was expanding. Now, we still argue about the expansion rate. Don't laugh, because that's a big deal in our field right now. But in any case, Einstein abandoned the static universe, and simple-minded, simplistic picture of it, everything is moving apart from everything else. It doesn't matter where you are, this is what you'd see. Now, of course, that doesn't mean you and I are moving apart from one another. Well, I can make it happen, but what it means is on the very largest scales, on the average, things are moving apart from one another. What do we mean by the Big Bang? Well, 14 billion years ago was the start of the expansion of the universe. The universe started out in a primordial soup made of many particles, quarks, leptons, bosons, and they were all very, very tightly packed on top of each other, very dense, hot, interacting universe. And then as time went on, these particles moved apart from one another. So the basic picture of the Big Bang is the universe started out hot, and it is cooling and expanding. One way to visualize it is with this raisin bread model of the universe. They tell me if you put dough in the oven, it rises. Probably some of you have tried it. I have not. And, and when that happens, if you had a bunch of raisins in there, they would be the analogs of the galaxies, then they would move apart from one another. Not because they're doing anything, but simply because they're going along for the ride with the expanding bread. But there's one very important difference between the raisin, well, there's more than one difference between raisin bread and the universe. But the point I want to make is the raisin bread has a center, But we don't think the universe does. We don't think there's any special point in the universe. Earth is not special, Sun is not special, Milky Way is not special. So on the average, no matter where you go, things look the same on large scales. I also wanted to talk about, speaking of the definition of the Big Bang, that, well, it's kind of a misnomer, because let's say we look backwards in time, and yes, everything's getting closer and closer together and more dense. Yes, this room, everything would be contract down to a point. But what if the universe is infinite, which is very possible? In that case, no matter how tightly you pack things together, it's still infinite. So it's not that we're contracting everything to a point. It's really not a point in space as much as a point in time, because if you do this contraction enough, eventually the density is so high, things are so tightly packed, that our laws of physics as we know them fail. You have to unify quantum mechanics and gravity, and we don't know how to do that. There are attempts, for example, with string theory. But so the Big Bang is really a limit to our knowledge as you go back in time. If you want to talk about an explosion, well, that would be, you'd have to put one everywhere. Where do we stand in cosmology? We've had some big questions for a long time, and some at the turn of the millennium. What is the geometry of the universe, the total mass and energy content, the age of the universe? But a lot of big questions remain, and the one I want to focus today on is what's the universe made of, because that one we really don't understand. But I wanted to talk about what we do know, so let's talk about the geometry of the universe. Well, there are three possible shapes for the universe. Obviously, I can't draw the universe, so I can only draw a lower dimensional analog. And for example, this one is a flat geometry. This is the geometry you did in high school or middle school or whenever you did. And for example, you draw a triangle, the angles in there add up to 180 degrees. This is standard as we know it. It's not two-dimensional. Remember, I've gone down to lower dimensions to draw it. But there are other possibilities. The universe could have lived on the surface of a sphere. And if that were true, then these angles in the triangle would add up to more. This is more than 180 degrees. The other possibility is a saddle shape, in which case the angles would be less than 180 degrees. So in 1930, when they first wrote down these equations, they realized these three possible geometries for the universe. And we now know the answer. It's a flat geometry. And let me just go ahead for a second. When I say flat, I don't mean two-dimensional. I mean, like, take a cube. In any direction you go to, you get straight lines just going ahead, and take that cube and expand it out to be very, very large. But the point is that the geometry is very simple. Here's another way to look at it. If you had a flat geometry, then when this guy shoots off two light beams, they just go off in straight lines. That's the flat geometry. But if you had a closed geometry, like if we lived on a sphere, they would come around and they would merge and bite him from behind. So the geometry that you learned in high school is still good. And how do we know that? We know that from looking at the leftover light from the Big Bang, which is called the cosmic microwave background, because these are in today's universe, they're microwaves. And if light travels in straight lines, then that would have implications for what the universe would look like. So this is the hot spots are regions where this light is, the red spots are hot spots, and the blue spots are cold spots, because this light from the Big Bang doesn't have exactly the same temperature everywhere. And so the question is, how does the light travel to us from those hot spots? Well, if the light is moving in a straight line, which would be the flat geometry, then we would expect the size of those hot regions to correspond to 1 angular degree in scale, if I look out that way. Yep, that's what we see. So this is kind of an indirect way to measure the geometry of the universe, but it is flat, and that was discovered around the year 2000. Now, from all these other peaks, we learn a lot more about the universe. This is one of our premier probes of cosmology in the universe today. In fact, here's Einstein's equations, and that's the famous equation from 1915, and I don't have a lot of equations in the talk, but what I just want to emphasize is you're connecting the geometry of the universe with the mass and energy content. So once you know the geometry, you know the total mass and energy density of the universe. You've seen these pictures. The Earth, for example, bends the space-time around it. That's the connection between the mass of the Earth and the geometry. Well, so what we get out of these cosmic microwave background measurements, the geometry of the universe is flat, means the energy density is this number, 10 to the minus 29 gram per cubic centimeter. That may not mean much to you, but it's really, really low. It's really diffuse on the average. Water on Earth is 1 gram per cubic centimeter. And I have a very funny story about how I tried to explain that to the Queen of Sweden, and it was a big fiasco. So ask me later if you're interested. Before I leave this subject, I did want to say that this is the same data from the American satellite WMAP, and in here, look, Stephen Hawking initials. Okay, well, so we know what the total is, but the question is, what are the pieces? And that leads me to the dark matter in the universe today. And it starts with a really bizarre fact, which is if you take everything we know about, the air you're breathing, your bodies, your chairs, the walls, the Earth, the planets, all of that, as you know, made of atoms, ordinary material, and all of that adds up to only 5% of the content of the universe. And we've got to figure out what the rest is, and the rest is the dark side. Good thing I'm wearing black. So the 25% dark matter and 70% dark energy, and we're trying to figure out what it is. But in fact, the idea of that dark matter is out there, that's been a problem for 90 years now. It was first discovered by Knut Lundmark in Sweden, and famously Fritz Zwicky, a Swiss scientist also working at the same observatory, the Mount Wilson Observatory. And what he looked at is galaxies moving inside a cluster. There's a cluster that contains hundreds of galaxies, and you watch a galaxy on the outer edge of the cluster moving around the center of the cluster, and that motion should be determined by how much mass is in there. And so what he found was very strange, that the galaxy that was moving around the outside was moving so fast it should have just escaped off. It shouldn't have been held to that cluster anymore based on the other galaxies he saw in the cluster. So the speculation was, well, maybe it's dunkle materia or dark matter. If you have additional material in there, that's holding on to that galaxy and keeping it sustained and contained within the cluster. And what does dark matter mean in this context? Simply that it doesn't shine, so he couldn't see it. There was a lot of debate back and forth for some time, but then, oh, you know, I have to tell this. Should I tell this, the famous story about him that everybody always, okay, in his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. Wasn't sure I should tell it, but here we are. There was a lot of debate, is he right or is he wrong? I have more funny stories about, ask me how I talked to his daughter many years later, but anyway, so then in the 1970s, it was really the work of Vera Rubin that clinched it. Looking at galaxies and finding evidence for dark matter in every single one. And at this point, everybody said, okay, dark matter is there. There's no avoiding it. There's no escaping it. And I'm going to back off of dark matter for a second and go to the analogy of the solar system. So let's look at the planets moving around the sun. All right, so the average speeds of the planets, here we go. We start at the sun at 0. And then as you move out, you get to the planets that are farther and farther away from the center. And this is the radii of their orbits. And then this tells you how fast they're moving. Okay, so the closest planet, Mercury, is moving the fastest. Then we get to Venus, Earth, Mars, da-da-da-da-da. I was supposed to remove Pluto, but I added a 10th planet instead. I knew Planet 9 was coming. Anyway, again, the speeds of these things are determined by how much mass is interior to their orbits. So here we go. If the sun were 4 times as massive, everybody would speed up, and they'd be moving twice as quickly. And the farther you go out, you notice that you drop off. They move more slowly as you move farther out. It was Tycho Brahe in the 16th century who made measurements of these planetary orbits. And he was a character. He lost his nose in a duel and wore a gold and silver replacement. And then there was people always said, well, he died at a dinner with the king because you're not supposed to get up until the king does. And he had too much wine, and he died a few days later of a burst bladder. But then all of a sudden there was this opposing theory that his student, Johannes Kepler, the names of planetary orbits became Kepler's laws and not Brahe's laws, that Kepler had him murdered. And they were going to test it. They dug up his body and they tested his mustache hairs for mercury poisoning. And this was, I don't know, 20 years ago. And no evidence. They did a massive amount of tests, no evidence of mercury poisoning. So I think it's true about the burst bladder. And again, I have too many stories. I'll tell you about how I have personal evidence of this. I totally believe this could be true. I was reprimanded, shall we say. Anyway. Okay, so that was rotation curves of the solar system, which wasn't about dark matter. But let's go back to dark matter and talk about rotation curves of galaxies. Okay, so here I've got a galaxy with something moving around in the galaxy. And just the same idea, the speed of this thing, whatever it is determined by how much mass is inside there. And, well, here's the equation. But the main point is, again, if there's more mass here, that makes these things speed up. Another way to look at it, this stuff would fly off unless there were enough mass in there to hold it in. So these are the observations that Vera Rubin made. This picture looks pretty similar to the one of the planets. And this is what they expected, that as you move away from the center of the galaxy, that the speeds would drop. But no, they found this flat rotation curves. Why? Because there's more mass. There's something else in there speeding it up. So they had to add in this stuff. This is the halo of dark matter. And when you do that, then you can explain, why are these things moving so rapidly around the center of the galaxy? There's some other mass in there. Our galaxy, the Milky Way, what does it look like? At the center, it has a supermassive black hole shown in yellow, so you can see it. And that thing weighs about 4 million times as much as the sun. The discovery of that went to the Nobel Prize for these two. And as you move away from the black hole, then you have the spiral arms of structure like a pinwheel, and the stars as you move away from the center. But now all of this is called the disk of the galaxy, and if I lay it on its side, here you go. And there's the center of the galaxy with the sun 25,000 light years away. All of that is only a tiny, tiny piece of the entire galaxy. So let's go to an artist's rendition of what the galaxy looks like. Here you go, the spiral arms, but then there's this giant, that's what I meant by the halo, the spherical object that is the majority of the mass of the Milky Way galaxy. So rotation curves were the first way this was discovered, but since then there's a million other pieces of evidence. One of them is also predicted by Einstein, gravitational lensing. Wherever you have mass, it's not giving off light if it's dark matter, but it bends the light behind it. Because according to general relativity, if I have a star here and I'm looking at it from a telescope here, the light will get bent. There's no kink, that's just my bad drawing. But the light bends on the way to the telescope, so you might think, well, the star's actually over there. But then you'd notice, wait a minute, there's a double image of the same object. What's going on? And you'd notice that these images are sheared. People use this to look at distant objects and figure out what's in front. Okay, so how much dark matter is there and what does it look like? There on your phone, there's an app written by a Michigan graduate student, Eli Reichoff, that has the correct equations of gravitational lensing, and you can lens yourself. More and more and more and more. This was my student. Now, let's go to Hubble Space Telescope data of actual lensed objects. Here you have a bunch of bright galaxies and the very distant ones, and in between them and us there's a lot of intervening material, dark matter. And as a consequence, you have multiple images, you have sheared images. There's a lot going on in this particular one. And then you use a computer to reconstruct, well, what dark matter would there have to be to make that happen? This is a different object in Hubble Space Telescope where the computer reconstruction has been done. Now this is a cluster containing tons of galaxies, and this tells you where the mass is. Well, here are galaxies sticking up, but there's a lot more mass. Look at that, there's a lot of mass also in between the galaxies inside the cluster. So dark matter is really everywhere. Then here's another piece of evidence. The bullet cluster is a pretty famous object. It looks like a bullet, hence the name. There are two clusters of galaxies that collided with each other, and during the collision, two different types of mass did two different things. The ordinary matter, the atomic matter, well, if you and I collided, we'd get stuck. We have electromagnetic interactions, strong interactions, and that's what happened to the ordinary gas. And then it gives off X-rays, and you see it in pink, so that it's shown in pink. You don't see it in pink. And so there you go, that's the ordinary matter. But then with lensing, they also found some other matter that behaved completely differently. It just kept going. It didn't get stuck. You can really see the difference in behavior of the ordinary matter and the dark matter. So I think I'm going to skip ahead. The evidence for dark matter goes on and on and on, and I only talked about some of it. But all of the evidence that I talked about, you know, the one that I didn't really mention is going back to the microwave background. This also has dark matter. In these other peaks, there's dark matter in the cosmic microwave background peaks as well. And you just can't argue with the existence of dark matter anymore. Pie chart of the universe, I showed it before, and the question, of course, is what are the pieces of this pie? So let's talk about what dark matter is made of. Pretty quickly, it was obvious that it couldn't be a lot of things that might be your simplest guesses, like gas or lumps of hydrogen or rocks or dust, because they would have consequences, observable ones, that just don't happen. And we also looked at small stars, planetary objects, and so forth. It can't be that either. Okay, so what is it? There's a lot of candidates out there. The two best motivated ones, theoretically speaking, are WIMPs and axions, which are the subject of study of a lot of people here also. But I did want to put on this list some of the other ones that are very interesting. Let me start with neutrinos. Neutrinos exist. We've known this forever. Why can't they just be the dark matter? Well, unfortunately, it doesn't work because they're too light. That was already known in the 80s because they're so light, they stream out of structure. They're going to prevent galaxies from forming. Not a good thing. We know they're here. Then, more recently, neutrinos in the standard model of particle physics were supposed to be massless, but they're not. They have really tiny masses. The mass is, do I have the number here, 10 billion times lighter than a proton, so really, really tiny masses. But it's non-zero, which is a big deal because it's not what was expected from the standard model. But in any case, they only make up 0.5% of the universe, not the 25% that we need for dark matter. And I wanted to mention work of Marilena's, who she's a theorist, but she looks at this is a really smart thing to do. Look at all kinds of different pieces of data to see, especially from cosmology, what can we learn? And it's very strange what the galaxy surveys are telling us about neutrino mass. So talk to Marilena if you want to learn about that. And I mentioned that this is in fact the only piece of physics that we know beyond the standard model, and there's many experiments trying to figure out correctly what the masses are, and that includes, this is work going on here. The Catron experiment, the double beta decay experiment, and then the cosmology that I mentioned at the beginning. All right, so neutrino physics is fascinating, and the Department of Energy is funding it heavily. However, it's not going to solve the dark matter problem. Primordial black holes have gotten very interesting lately, and the reason for that is LIGO. Let me tell you briefly what primordial black holes are. Very, very early in the universe, there could have been a time when there was an overdensity, that there was a lot of mass in a small volume, and then it would collapse off into a black hole. And where could this happen? Well, for example, at phase transitions, such as when ice melts and it turns into water, and when things like that happen, that's when you get these fluctuations that could lead to primordial black holes. Now, the reason these have gotten so much attention lately is because there are now merging black holes that have been discovered. And this is a really important new field of physics, the study of merging black holes with, for example, the LIGO detector. And these could be primordial black holes. So I did have to have a brief aside on this subject. What are gravitational waves? Anytime mass moves, move your hands, you're going to make gravitational waves. That's kind of uninteresting to the amount that I've just produced. But when black holes merge, then you get the big ones. That's what LIGO is seeing. And so what they do is they stretch matter in one direction and expand it in the other. A broken slinky or something, I don't know. And that's what's now been, that was measured for the first time in 2016, immediately leading to a Nobel Prize. And the idea is you have these two arms, each 4 kilometers long. One of them gets a little bigger, the other one the length gets a little shorter, by the fraction of the size of a proton when the gravitational wave comes by. My God, the fact that this is doable is phenomenal. And there's part of the gravity group here, their role is to make sure that there's stability here when these measurements are made. So this is a very important contribution from here. Okay, however, I want to get back to the 2 candidates that I said have the best theoretical motivation. And that would be WIMPs and axions. And the main point of this slide is simply to say that the reason that we like them is because they weren't invented to solve the dark matter problem, not at all. In fact, they were automatic byproducts of other particle theory that people were working on. I'm not going to say a lot about axions. I do want to say that they're very light particles. They were independently proposed by these 2 guys. I'll say a little bit more about Steve Weinberg in a second. So the theory of strong interactions is what holds your nuclei together. There was a problem with that theory, and if you solve that problem, you automatically get axions. Okay, so that's nice, killing 2 birds with 1 stone. And I have to have a slide about Steve Weinberg, who was one of the most brilliant, most wonderful and brilliant people of our time, and one of the founders of the standard model of particle physics. And unfortunately, he died 2 years ago. And it is in his honor that we have started the Weinberg Center for Theoretical Physics. I'm the director of that. But anyway, so I just had to mention Steve Weinberg in this talk. Okay, so on the subject of axions, this is the mass of the axions. This is how strongly they interact with light. This yellow line, this yellow swath here, that is the thing that would solve these problems with the theory of the theoretical problems with strong interactions that I talked about. And well, people started thinking about, okay, instead of just axions, let's have axion-like particles or ALPs. And then all of a sudden it opens up all these other possibilities. Maybe they come from string theory or somewhere else. Not as strongly motivated as the stuff in the yellow curve. And here's where I mention, these are people, I like to show slides either of my people or of people here. So Luca Visinelli wrote a nice review. And Masha, I'm going to get your name wrong if I try to pronounce it, but she's a theorist here. You guys are so lucky to have this amazing theorist here anyway. And so she's working on the theoretical aspects of these things and connecting to experimentalists. Okay, so back on the QCD axion, the yellow swath, well, here we go. ADMX is the one that's most interesting as far as probing this parameter range, and guess where that is centered? Here. It's the work of Leslie Rosenberg and Gray Ribka and some wonderful students and postdocs that I met. And anyway, so I just wanted to mention that. Now I want to get back to WIMPs. This is the thing that I've worked the most on. Okay, what does WIMPs mean? Well, it stands for weakly interacting massive particles. A reporter once asked me, so I now know the answer. Billions pass through your body every second, and one hits one of your nuclei roughly once a day to once a month, depending on the details. But it's not doing anything to you. Why? Well, it doesn't feel strong forces, it doesn't feel electromagnetic forces, it doesn't give off light, so you know that's true. Yes, it feels gravity. Okay, we know of 4 fundamental forces. The remaining one would be the weak force. The postulate is, if you have a particle that feels the weak force, can that work as the dark matter? And the answer is yes. And these things, by the way, weigh about 1 to 10,000 times as much as a proton. This is not a very helpful slide, but basically the point of it is, weakly interacting massive particles, many of them are their own antipartners, and we know how to calculate how many there are. Let's go back to the early universe. It's a fluid, it's a thermal bath of stuff, and we know how many there are of everything. And we can predict how many of these annihilations would be happening, and these annihilations are via the weak interaction. So that's the only ingredient in the story. And then, well, as the universe expands, those interactions stop, and how many are left around today? And the answer is, it comes out right. Okay, you get the right answer if the dark matter is weakly interacting. Some people call that the WIMP miracle. The other reason, as I said, is that it's already there in it's a byproduct of other theories, such as supersymmetry, where every particle we know has a partner. And this is the standard, these are standard particles, quarks, and this is the standard model. And then they're each one that would have a heavier partner, which is why we don't see them regularly. But the heaviest one decays to the next one, until you get to the lightest one. The lightest supersymmetric particle could be the dark matter that makes good WIMP candidates. Well, this is a field where people are looking in with 3 prongs. Fourth prong, dark stars. That's mine. I got to tell you later. So you either make it, shake it, or break it. And these are 2 dark matter particles and 2 ordinary matter particles, and we have the weak force in between them. And you get all these different varieties of interactions. So the first way is to make them. Now let's go to the Large Hadron Collider at CERN, the particle accelerator in Switzerland, and let's go skiing. So you have this ring of protons at 27 kilometers around, where the protons are accelerated in opposing directions, and eventually they collide. And it's controlled exactly where they collide, and that's where the detectors, the ones who are interested in ATLAS and CMS, and you study what comes out in the collisions. Just a few pictures. She is Fabiola Gianotti is the Director General at CERN, ATLAS detector at CERN, and this university, the physics department here is involved with the ATLAS experiment. You'll notice the physics department is involved in almost everything I'm talking about. The CMS detector, Peter Higgs was the one who was one of the proposers of the Higgs boson, and indeed the LHC did find the Higgs boson. There it is. Whoop, this little bump, it weighs 125 times as much as a proton. And the second major goal at the beginning would have been searching for supersymmetry, in addition to, of course, searching for whatever else interesting you could find. And the way that would work is when these protons collide, you'd have supersymmetric particles come out, decaying in a chain to lighter and lighter until the lightest one escapes detection, and then the energy wouldn't add up properly, and you'd notice that. So unfortunately, there has been no discovery of supersymmetry or of missing energy or dark matter particles, which means possibly that the particle masses are pushed to higher masses. It doesn't rule, so supersymmetry is not ruled out, but it's not seen. The second way to look for these particles is laboratory experiments here on Earth. The basic idea being that, well, I mentioned there's billions going through your body every second. That means in the galaxy there's a lot of these things. And if you build a detector, here's some atom making up my detector, and along comes a WIMP. It scatters off of that atom, and it deposits a very small amount of energy. And the name of the game is to detect that small amount of energy. Very small amount of energy, very infrequent interactions, so very tough game. I have to mention in this talk my wonderful PhD advisor, David Schramm, who was one of the founders of the entire field of astroparticle physics. I switched fields several times, but was totally drawn to this very inspiring field, this inspiring man in this inspiring field at its beginning. And if there are grad school students in here, find an inspiring advisor like that one. Then that was me in grad school. Then as a postdoc, I worked with David Spergel and Andre Druckier. We were among the first to study the basically this process of WIMPs interacting with nuclei. We wrote the second paper ever on it. I did Feynman diagrams, the particle physics, he did the astrophysics. And so what would you expect out of this? Well, we made calculations and people thought, experimentalists said, yes, we can do this. And they started building. And this has been an effort for a long time now. One thing is you have to be deep underground. Otherwise, you have to shield from ordinary stuff. Yes, cosmic rays are ordinary particles that are hitting us all the time, and yes, they can kill you. But, well, it's actually a big deal, like for astronauts. When you get away from the atmosphere, there's too many cosmic rays hitting you and you get cancer. It's a form of radiation. But you have to go into deep underground laboratories to shield from these things, so about a mile underground. And at this point, it's a worldwide effort all over the place. And I'm focusing today on the Gran Sasso Tunnel in Italy, which I got to see for the first time in July. You go drive down into this tunnel, and there's all these experiments you've ever heard of. A lot of the experiments I've heard of, they're all in there. It's pretty cool. Okay, so of all those experiments, there's only one. This one's in the Gran Sasso that has been claiming detection. Oops, that was me. And what they used is an annual modulation of the signal, which is something we proposed. We predicted that because as the Earth goes around the sun, the signal should go up and down with the time of year, peaking in June, minimum in December. Well, that's exactly what they see. There's a lot more data. You just go on year after year, you see the same thing. They definitely are seeing an annual modulation. But the question is, what is it? They won't share their data, which is unheard of. And yes, leaders of various, PIs of various experiments. This is just to point out the fun that you have dealing with the people. There's a lot of personalities in this field. Juan Collier, I'm a Spaniard caught between two Italian women. I swear to God, I should write down everything he says. He's so funny. Okay, so, but here's the problem. Dama is the only one to see anything, and these other experiments don't. So, but how do we compare them? It's a little tricky, because Dama is made of sodium iodide, and these other experiments are made of other things. If you make the most simple assumption, then you can plot them all on the same plot. And here, the mass of the particle should be 1 GeV is like the proton mass should be. So you should be in here, but then because these xenon experiments don't see anything, you should be below these lines. So is it ruled out or not? Well, what had to happen, because it's now happened, is other groups had to use the same material. And yeah, this is something that just came out, new results. The other experiments are not confirming this modulation. Okay, which that's kind of sad. But it's not ruled out, but it's getting there. Okay, so what's coming in the future? Well, what if we could look at lower dark matter masses than the ones I've been talking about? And that's where the DOMIC experiment also, which is Alvaro is leading the effort here for the DOMIC experiment. That's going to look at lower masses. Very interesting. I also wanted to talk about a new direction that we proposed in 2018, paleodetectors. What if instead of having, oh, I didn't mention this, the xenon detectors, the ones made of xenon, they are 4 tons of material. They're really, really big. So what if instead of having 4 tons of detector, you have small rocks, but they're from deep underground and they've been collecting tracks for 1 billion years? You're replacing size with time. So they've been sitting underground, avoiding cosmic rays, and then you pull them up and you have a look. You look for defects in the crystals. Well, we thought we had this brilliant new idea, but 30 years ago, somebody had done the same thing in MICA, the Dan Snowden IFT. However, they couldn't analyze those defect tracks because they're too small, they're nanometer. Guess what we have 30 years later? Nanotools, so it can be done. And in addition to going after dark matter, you can also study neutrinos from supernovae, cosmic rays, you can monitor nuclear reactors. There's a lot you can do with these things. And, you know, you write a theory paper, but this one didn't go away. My student and postdoc really pursued it and brought in all kinds of people from Stanford and Karlsruhe Institute of Technology. All of a sudden, we're having biannual meetings, and better than that, money. So in fact, there's at the University of Michigan, Josh Spitz got money to study 1.5 million from the Moore Foundation to study neutrinos from cosmic rays. And we got an NSF grant for 3.5 million very recently for this paleo detector stuff. It's not me, it's for the experimentalists. But I just think that's really cool. So this is another thing to look forward to in the future. All right, we have fun. Another way to search for these particles is called indirect detection, where you're looking for, well, I guess I'll just leave the sentence right here. It's useful searching for, if these WIMPs are their own antimatter, they annihilate, and you look for the annihilation products. Let me show you a diagram of that. You have two dark matter particles, and they go through a chain of stuff, and in the end, what you always get out, neutrinos, these are high-energy particles of light, high-energy photons, and positrons. And I'm not going to tell you about all the efforts that are going on experimentally, but all three of these are being looked for, including IceCube at the South Pole, which is a wonderful neutrino detector. There's the Eiffel Tower for comparison. So many kilometers down in the ice, you have these strings of phototubes. They're finding very interesting neutrino physics, but no hints of WIMPs. The one thing that does have something interesting from the dark matter point of view is the Fermi satellite. They study the gamma ray sky. Again, gamma rays are high energy photons. This is the gamma ray sky that they see. And there's the center of the galaxy with these double bubbles that a friend of mine identified, actually. But the question is, smack at the center, is there something interesting going on? It looks like there might be. There's an excess. There's too many gamma rays coming from the center of the galaxy. And if you subtract off all the stuff you do know about, you're left with, yeah, there's extra stuff from exactly the center of the galaxy. Is that from dark matter annihilation? So are you seeing photons that came out of two dark matter particles annihilating? The reason the galactic center is interesting is because at the center there you have a lot of dark matter. The dark matter tends to concentrate at the centers of things. So that's why that's a good place to look. Oh, good. I do have time to talk about dark stars. This is the thing I'm excited about. This is an idea that we proposed in 2007. It was me and Doug Spoliar and Paolo Gondolo. And we named it after a song from Crosby, Stills, Nash & Young, not the Grateful Dead one. And we found out about this film later. It's a cult film, and it's really bad. So the basic idea here is that these would be the very first stars to form in the history of the universe, and that would have been 200 million years, when the universe was 200 million years old. The very first stars formed inside protogalaxies, and they formed smack in the middle of these protogalaxies. When I say proto, it's because these things are going to merge together later on to make galaxies. And we thought, well, if you're smack in the middle of a protogalaxy, well, there's a lot of, again, as I was saying, where you're at the centers of galaxies or protogalaxies or anything, there's a lot of dark matter. What role does the dark matter play? And what we came to realize is that you could end up with a star that is powered by dark matter annihilation rather than by fusion. You know, before I tell you any more of the details of how these things form, let me make it really clear. These are made almost all of hydrogen and helium from the Big Bang, because nothing else had been formed yet, no other elements. And dark matter constitutes less than 0.1% of the mass of the star. So they're atomic matter powered by dark matter. Let me go back to the basic picture of how they form. Smack in the middle of this protogalaxy, you've got a cloud of hydrogen that starts to cool and collapse on its route to making a star or whatever. But it pulls in a lot more, even more dark matter with it, and that dark matter annihilates. When you have a lot of dark matter together, those particles annihilate among themselves. And those annihilation products, the same ones I was talking about for indirect detection, well, neutrinos escape. But most of the annihilation gets stuck inside this cloud. So it's like you're taking all of the energy that used to be in the mass of the dark matter and you're dumping it as a heat source into this cloud. And so that cloud, first of all, the cloud stops expanding, and then it took a year to realize it's a real star. There are, what does a star mean? It means, well, there's 4 equations of stellar structure, and all of them are satisfied. You're in hydrostatic equilibrium, you're in thermal equilibrium, so the pressure is balanced. The mass tries to make it collapse, there's a pressure to balance it, and so on and so forth. So it's an actual star, but it's a really, really weird looking star. Okay, so these things are big, puffy objects. Puffy meaning that their size is enormous. The radius is enormous. So the radius of the star is 10 times the distance between the Earth and the Sun. And the mass initially starts at the same as the mass of the Sun. But you've got this weird thing with dark matter annihilation throughout. There's no core. There's no fusion. It's not hot anywhere. Cool, 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 all the way to the outside. And that means more and more mass can accumulate onto it. It accretes, and it grows, and it grows. And eventually it can grow to 10 million times the mass of the Sun, 10 billion times as bright as the Sun, which is, wow, I mean, these are really, really very massive early objects. And we're still talking very early in the history of the universe. Now that leads to 2 interesting consequences. I'm going to skip ahead and talk about one. One is that if you have a million solar mass star, once it runs out of the dark matter fuel, it's going to collapse to a million solar mass black hole, a black hole that weighs 1 million times as much as the Sun. That's a supermassive black hole, and that is wonderful because it explains the big black hole problem. There's so many early supermassive black holes that people really struggle to understand. In fact, the center of every galaxy has a supermassive black hole. Maybe this has something to do with that as well. So first you're solving the big black hole problem with these massive stars, and then I also say, well, they're not only massive, but they're also really bright. John Mather, who was the speaker last year, in 2010, he said to us, he was, at that point, he had proposed the James Webb Space Telescope. It was going to happen. And he said, tell us what to look for with the JWST as far as what are dark stars going to look like. So we did that. And the thing that I do want to say that one supermassive dark star would be as bright as an entire early galaxy of stars. And it would be observable. So we showed that these are the filters. How bright these things are? Well, these are the filters of JWST, and you'd have to stick out above the filters. Yes, you do, so you could see them. We did a lot better work than this, but one shows it in the most simple fashion. And a year and a half ago, we found candidates for dark stars in the James Webb Space Telescope data. There are now more spectra, but at the time there were only 5 with spectra, and we realized that 3 of them could be dark stars. And this tells you the redshift, how far back in time these things are, and this really, really early in the history of the universe. And yeah, so we compared, here we go, here's a spectrum. What is a spectrum? It means how bright are these objects in a given wavelength or frequency of emission. Then the predictions for dark stars are this blue curve, and the data are the black dots. It fits. Not cleanly enough to prove it's a dark star versus an early galaxy, but in the future, a lot of things are going to happen. With a big one will be lensing, the same lensing I've been talking about. That one of these bright early objects, which could be an early galaxy, could be a dark star, will have a lot of mass in front of it, which will make it it'll amplify what we see. It'll make it bigger and brighter, and we'll see enough detail that we'll know, is it actually a dark star or is it an early galaxy? So we have much more data to look forward to. And the other nice thing about the dark stars, they solve the big black hole problem. They also solve a problem for the standard model of cosmology, which is that right now JWST is finding too many galaxies and too massive galaxies. Okay, let's take some. We'll be happy to take some as dark stars. So that's what I've been very excited about lately. And, well, I've talked about many ways to look for HIMPs, the WIMPs, the standard 3 mechanisms of the 3 prongs, and then also looking for dark stars. Well, I'm running out of time, so I'm just going to end with a 2-minute discussion of dark energy, the big beast. you might as well call it gobbledygook for all we know about it. We don't understand it at all. It's a complete, it came as a complete surprise, a paradigm shift, and it's still not understood. It's not understood on theoretical grounds. And on experimental grounds, there's now some hope to figure out, oh, is it the same? Did it change with time? As I look back in time, was it a little bit different? And there's some people claiming evidence for that. So on the observational side, there's some progress, we hope. Well, what do we actually know about dark energy? Well, when we talk about matter, dark matter, ordinary matter, all of that feels gravity. It's gravitationally attractive. Dark energy has the opposite behavior. It's causing galaxies to accelerate apart from one another. The expansion has been known since the time of Hubble in 1929, but what the heck? Now it seems as though that expansion is in fact accelerating. In other words, the galaxies on the average are accelerating apart from one another, which means you better hurry up and do as much astronomy as you can before they've gotten too far away from us. And so here comes the joke that goes along with that. So again, the only thing we know is that dark matter, that matter is attractive, and whatever this stuff is, and we don't know what it is, well, it has the opposite behavior. It causes, anyway, so this was a panel that I was on. The three of us were talking about dark matter. This is at the World Science Festival in New York. They were talking about dark energy. And I said there's only one thing we know about these. Here you go. Yeah, I'd thought of that before I got on that stage, I have to admit. Okay, so I'm going to stop here, and this is from my book, The Cosmic Cocktail, 3 Parts Dark Matter. What do I mean by 3 parts dark matter? Well, if you're going to make a drink of 10 ounces, sounds reasonable, then here are the ingredients. Well, not much supermassive black holes, 1/1,000,000th of an ounce, et cetera, not much stars or anything else, really, not enough neutrinos. Yeah, dark matter and dark energy, that's the biggest part. It's really 2.5 ounces. Forgive me, I rounded up because I like dark matter. And see, shaken, not stirred. And I'm going to stop there.
Hi, I am Alberto Oria, and we're going to start now our Q&A with Dr. Freese. So if you're interested in asking a question about dark matter or the Queen of Sweden or anything else, please line up at one of these 2 microphones on the side, and we'll take your questions for the next 15 minutes or so before the book signing. So please.
I did want to say that Marilyn had mentioned this, that after the 15 minutes of Q&A, we do have the books back here, and I'll happy to do a book signing if you're interested. And I'm a little worried about the acoustics because I couldn't understand a word you just said. We shall see.
Hello, my name is Rick DeWitt. Could you please go back to the slide that had the large halo around the galaxy, the dark matter halo?
The artist rendition one?
Yes. Way back there.
That's way back. It'll take a while.
Back. So when we do computer simulations of galaxies and the rotations, we use Newton's law of gravity. Newton's law of gravity is based on spheres. So this halo is a sphere. So if indeed our Newton's law of gravity is not applicable in this situation, the error would come from the modeling error of improperly using Newton's law of gravity, and the error would look spherical, just like that.
Well, you're right. On macroscopic scales like this, Newton's laws are fine. And in fact, people thought, instead of dark matter, what if we modify Newton's laws? That was called MOND, Modified Newtonian Dynamics. And the idea behind that was it was initially just supposed to explain those rotation curves, those flat rotation curves. And the idea was that when you get out, that Newton's laws are fine here, but as you get out to very low acceleration out there, that you change the laws a little bit. And that actually does explain rotation curves just fine. But I showed you about another 5 pieces of evidence for dark matter, and it does not explain those as easily. So that was just a simple equation mocking up what a rotation curve what Newton's laws should change with. Later versions of it became more sophisticated mathematically. And in the end, in order for those to work, you have to have new fields, and you still have to have dark matter. There's no avoiding it in order to explain like the cosmic microwave background. You absolutely have you can't avoid dark matter with these modified versions.
The point is that if you were going to make up a fudge factor, that the fudge factor would look like dark matter, and the dark matter would look spherical, because your underlying theory is spherical, and that's the thing you're fudging. So it's possible that dark matter doesn't exist at all, and the model of gravity is incorrect.
Well, the only variant of that there is a variant of that did make sense mathematically, and as I was saying, it doesn't really work with the observations. You have to have new tensor, new scalar, and new vector, new tensor, new scalar, and dark matter. And that's not, I don't think a lot of people are working on this anymore without a dark matter component.
Hi, thank you for your talk. I'm sorry if my question's not totally formulated here, but on the topic of dark stars, where we've got this dark matter that seems to be clumping more than regular matter, and is then heating up the matter. It feels
No, I mean,
odd.
I don't know what you mean by clumping more. It's just ordinary gravity for both of them, so no.
Well, but in a dark star,
Oh, there's more dark matter at the center of a galaxy than there is farther out, yes. It's pulled in towards, there's more at the center. That's,
okay.
Yes.
Well, I guess that idea of the dark matter annihilation exerting the pressure on the regular matter makes me wonder about how dark matter is
That's not really the way it works either. So the
okay.
Yeah,
So,
it's more
okay.
sophisticated. I just gave a 2-minute overview.
Yeah.
But the dark matter annihilation products then they thermalize with the star, and you can think of it as an additional heat source for the star.
Okay.
And if you want to satisfy all the equations, then you end up with these weird things that we got.
So in the early universe, then, we do still need the dark matter to provide the structure for the seeds of the first galaxies?
Yes.
Yeah. Okay.
Absolutely. You may have noticed I skipped over a bunch of slides. This always happens. You decide I don't have time for this, and then, all right, I'll just talk about this. All right, so initially, if the universe were entirely homogeneous, and it was the same everywhere, then nothing interesting would ever happen. But no, we think that there were some regions that were a little bit denser than their neighbors, and these are called density perturbations, and it all came out of an early inflationary epoch, the quantum fluctuations, da-da-da. It doesn't matter for the current discussion. There were regions that had more dark matter in them, or more any kind of matter in them, which means they would gravitationally attract in more stuff. And those regions would grow until eventually they became galaxies. Neighboring regions would lose out, and they would end up being voids, which are underdense regions today. There are simulations that you can do of this, so let's just put in these. So this is when the universe was, this number means that this was 30 times, length scales in the universe were 30 times smaller than they are now, okay? And that, let's say you start out with things almost, this is a dark matter only simulation where these bright regions are clumps of dark matter, and they're almost uniformly distributed, but not quite, because you have slight overdensities and slight underdensities. Okay, and so the dark matter particles will then collect together to make galaxies, clusters, and larger structures. So let me show as time goes on what happens. Because purely gravity, the dark matter clumps more and more. And in this simulation, this is what you end up having, and this is a pretty good match to reality. You have filaments of structure, and the galaxies are at the nodes of these filaments, And this is all dark matter starting out almost uniformly distributed, not quite, and then this is what you get. And so we get smaller structures, which then merge together to make bigger ones, and so on and so forth. So I forget exactly what your question was, but this whole picture doesn't work unless you have dark matter. It would take too long. If you only had ordinary matter, galaxies wouldn't exist yet. This dark matter can clump way earlier than ordinary matter, and it sets the stage, and ordinary matter falls in to these regions of overdensity.
So first off, it was very interesting to hear your presentation. I was curious, so, you know, unfortunately, like with our human eyes, we can't see dark energy, we can't see dark matter, and like
That's the whole point of the word dark in there, right?
I know. Well, like, and then we also can't like go back in time to the Big Bang to like see what really went down. So like, what are some of the challenges that come with like doing research, like just having to rely on detectors? Like, what are some of the challenges that come with that?
You know, I'm not sure if this is what you're asking, but one of the reasons I went into cosmology is I was absolutely blown away when I heard this is a long time ago, a graduate student give a talk about Big Bang nucleosynthesis. Okay, when the universe was 3 minutes old, something happened. Before that, you only had neutrons and protons around. But then at 3 minutes, you start to make more interesting things. You get a neutron and proton, when they get together, they make deuterium. And you get a couple of those together, you get helium. Okay? And so you end up with only 4 different types of elements that form at that time. But the predictions for what you get vary by 10 orders of magnitude. In other words, a quarter of the universe should be helium-4, and 1 part in 10 to the 10 should be lithium. And in between are a few other things. And guess what? They've measured, these are predictions from 3 minutes after the Big Bang, and the predictions are dead on. It's just, and that blew me away. I'm like, whoa, this is not science fiction. You can make predictions from 3 minutes after the Big Bang. You can't see that far back, you know. But we have leftovers. We have vestiges that we can use. And so this picture, we understand it really, really well, which is pretty cool. But maybe that wasn't your question, but.
Back to skip slides, I'm interested in the evidence for primordial black holes, and didn't microlensing
I'm having a lot of trouble hearing.
What is the evidence you mentioned for primordial black holes, and wasn't microlensing studies not finding them an issue against them?
Oh, did you say
primordial black holes?
And it's, oh yeah, are primordial black holes, there are plenty of bounds on constraints on primordial black holes. So primordial black holes could be a variety of different masses, and for each of the masses, people think about, well, what would that do? So for example, I think you were talking about microlensing, which again, it's lensing, that as a primordial black hole goes by, it acts like a lens, and you see a blip, and something looks temporarily brighter. And so then, but that's not seen, and therefore you get bounds on how many black holes of a certain mass there could be. So there's all kinds of bounds like that, yes. And there's a huge effort going into getting it right.
What was the new evidence for primordial black holes? You said
I can't hear a word.
There was new evidence for primordial black holes, you said?
What did he say? Oh, well, I mean, the only thing I was talking about was evidence. There are the emerging black holes are being studied all the time now in LIGO, and that got people interested in, well, where did those black holes come from? But specifically for primordial black holes, okay, my former postdoc, Florian Kühnel, would give you 5 pieces of physics that or astronomy maybe, that whatever, I don't know what to call it, but that you could explain with primordial black holes on all different size scales. And to him, so there are people saying, yes, it's got to be primordial black holes. I'm not the expert. And is there definitive proof of primordial black holes? No.
Hi. First, I want to thank you for your talk. And I'm an physics undergrad here, and then I'm working on research comparing self-interacting dark matter and cold dark matter. Mm-hmm. And I'm just thinking about
That's a topic I didn't get to, but.
Yeah. So.
By the way, dark stars would work with self-interacting dark matter too. But anyway, go ahead.
Yeah, so I'm just wondering, like, the WIMPs that you're talking about, like, the level of, like, self-interacting between them, could they be considered as a form of self-interacting dark matter? And then could they possibly solve, like, core cause problems or like stuff
No,
like that?
WIMPs are straight up cold dark matter. Self-interacting dark matter is much more strongly self-interacting than that. But very interesting. That would solve some of the, there's some conundrums people see, or maybe they don't see. There's argument about the observations also, but self-interacting dark matter was proposed as a dark matter possible candidate. It's very interesting.
Thank you.
Mm-hmm.
When you're trying to detect WIMPs, how do you know you're not blocking them with those shields from to protect from the rays?
Can you repeat that?
When you detect WIMPs, how do you know you're not blocking them by putting them underground, shielding the cosmic rays?
Oh, well, WIMPs don't, something that has electromagnetic interactions doesn't get very far. It hits, that's just like you and I, when we hit, we're not going to get very far. And so they don't get, the cosmic rays, which have electromagnetic interactions, do not get through the Earth. Neutrinos do, WIMPs do. They don't interact as much. The weak force is just, that's why it's called weak. So they don't hit anything on the way to the detectors. I like your bow tie.
Okay, so if I don't think we have, should we close that? Yeah.
And I
So-
like your question.
Okay, so since there are no more questions, then we're going to end the lecture here. Please, let's thank Dr. Freese once again. Okay, and so we will now have a book signing by Dr. Freese here on the stage. There are books for sale if you'd like. They're $20. I want to thank everyone for coming. We don't have a speaker for the spring yet, but there will be a spring lecture. So please keep checking our website, frontiers.uw.edu, for updates. And there are opportunities there to support our department and make sure that the series remains free for everyone. Thank you. Have a good evening.